This is Dr. Wood with Citadel Civil Engineering. This is Statics, CIVL 202. We're looking at Learning Objective 4, discussing friction today. And so with that, we'll jump into it. As a reminder, we're going to be using the concepts we talk about today in statics in our future classes. I can say for certain that we'll talk about friction in dynamics. And so this is a concept we'll want to have ready and available. This is one of the other topics that kind of gets shoved into the side of statics. Nevertheless, we're going to be using all of the statics concepts that we've learned to date when we actually work friction problems. And so here's some examples of how friction can work. So this is one of my favorite examples as a civil engineer to look at a retaining wall structure. Now this retaining wall structure is a mechanically stabilized earth retaining wall. The basic idea is that the front concrete facing holds soil in place. The soil presses down on, or the panels are then attached to metal strips or grids that lay in the backfill, and those hold the panels in place, and then the soil squeezes on those strips and holds them in place using friction. And so we can look at the design layouts that come from the AASHTO manual for designing these types of structures. So you can see where we have those lateral strips and then the facing, and it creates one large reinforced earth block. This is actually the loading diagram that we look at. And so as a statics student, you should get excited. This comes out of the very code that people use to design retaining wall structures. And it has those distributed loads. So for example, you can see over here, this H over 3. What's that H over 3? Well, that's 1/3 base, or 1/3 the height in this case, to find the centroidal location for that triangular distribution. Likewise, the H over 2, that gives us the traffic surcharge. So there's all these loads that get applied to the retaining wall, and then as well as gravity of the whole block to resist both overturning and sliding. And so that sliding is going to engage friction along the bottom of that block. Finally, this is a document that first developed the MSE wall concept in the 1960s. And they have this F here where we have normal forces and a differential frictional force. And this F, this little curly F here, that is a coefficient of friction between the soil and the strip that's holding it in place there. And we're going to learn about how that coefficient of friction works today in this lecture. So that kind of gives you a background. Hopefully it gets you a little excited about the types of things that civil engineers will use friction for. And so with that, I want to go ahead. We're going to be working this problem together on the Zoom meeting, but I want to blow this up a little bit and put some notes on the board for you on dry friction. So we're specifically talking about dry friction in this class. Turns out when you add liquids to the system, things will change, and they all change a lot. It depends on the viscosity of the liquid. It gets a lot more complicated. But when we talk about dry friction, we can make a simplifying assumption that comes up with this coefficient of friction. So dry friction is simply the forces on dry surfaces, hence the dry part. And this is the key, the forces on dry surfaces that resists motion. And so friction is always trying to keep things from moving, which is great because we love it when things don't move. Yay, nothing moves. And so friction is going to be resisting motion. And so in this class, this lecture today, we're going to start talking about motion a little bit, but really it's static, so nothing moves. It just almost moves. And so as we think about that, let's look at the equation of friction, and we'll often abbreviate this as EOF. Now, we've called this an equation of friction, and it's in page 7. It's on page 73 of your FE reference handbook. But this is really not an equation. It's actually an inequality. And so the way that we've got this written from your book is something like that. Okay, so we've got friction over here. The frictional force that's resisting motion is less than or equal to the coefficient of friction, mu sub s, s meaning static friction, right? Static friction, as opposed to kinetic friction, something you probably talked about in your physics class, times the normal force. So that's going to be perpendicular to the frictional force. Sometimes I like to write this frictional force. I'll just do F sub Ric to remind myself that it's friction, but this F sub S is indicating a static coefficient of friction. The other thing we can note about this, and we'll actually prove this in the problem that we work on the Zoom meeting, but we can also talk about the friction equation this way, where this is phi sub S, or the static, or the friction angle, friction angle. And so what this is going to be is, if we think about a surface like so with some object, right? The normal force is perpendicular to that surface, and the frictional force is resisting that motion. And if we combine these two, we'd get this guy here, right? Right? So if we did square root of the sum of the squares, and it turns out this angle in here, that's the friction angle, phi sub S. And so we would look at that F sub S, so the frictional force here divided by over the normal force is equal to the tangent. That tangent of phi is equal to the coefficient of friction. This tan phi concept here gets used a lot in soil mechanics, where we'll talk about an internal friction angle. And so again, this is going all the way to your senior year, where you're looking at your geotech courses. Tan phi, an internal friction angle phi, is going to be used a lot when we do that. And so it's this little angle in here, the friction angle, that describes the relationship between our friction force and our normal force. So that's what we're looking at there, page 73 of your FE reference handbook. Now, it turns out that the way we use this introduces three different types of friction problems. And we want to be able to classify these types of friction problems. Your textbook does a good job of this in the chapter on friction. The first type of friction problem is going to say that we have no impending motion. Okay, let's create a friction problem. Right here, if we look at this, I think you can just barely see that on the bottom of the screen. What I have is, I have a little ramp here, okay? And I've got a little block with a spike on there that can increase the angle of the ramp. All good? That makes sense. I've got some other blocks that I can put on the ramp, like so, okay? And if I put this on the ramp, and we're looking at it here, we've got the weight, and we've got the normal force that's acting perpendicular to the ramp, like a roller would. And then we have the friction force, in this case, pointing up the ramp. The object naturally wants to slide down the ramp, right? It wants to try and move down the ramp, but it's pushing up. And in this case, because there's no apparent impending motion, nothing's about to happen, it's just sitting there, it's looking nice and happy, what we'll find is that we can solve for it using our equations of equilibrium. So the idea is that our equations of equilibrium, the number of equations of equilibrium, will be equal to our number of unknowns for a given problem that has no impending motion, okay? So in this case, we can think about some of the forces in the X and some of the forces in the Y. If we're modeling it as a particle, that would give us everything we needed to solve for the normal force and the frictional force. If we use some of the moments, we can actually calculate where that frictional and normal force, where the centroid is that it lies. If we look at this equation over here, we'll notice that the relationship between the normal force and the frictional force doesn't have area in there. And it turns out that the contact area doesn't change this relationship. What it changes is the intensity of the distributed load. So there is a distributed load acting across the bottom of the force there, both a normal pressure and a frictional pressure, right? So if you think about, like, if you try to slide your hands, there's pressure at different points. But if you calculated the area, or the total force, the total normal force, the total frictional force, this relationship still holds. If you do some of the moments, you can figure out the centroidal location for that total frictional and normal force as it acts. And so those are kind of some of the big ideas that are going on there. So just to address it really quick, I know a lot of people think, oh man, but why doesn't contact area matter? I mean, we know, my favorite example is that performance race cars have wide tires. So clearly that's to get more frictional force, right? Well, it turns out that the reason for that wide tire, this is a little aside to frictional force, is that it has to do with changing the coefficient of friction, not adjusting the amount of pressure acting on the tire. It turns out that the coefficient of friction for rubber tires is highly dependent on the temperature of the tire. So this is why in NASCAR during slower laps, you'll see them swerving. What they're doing is they're trying to keep their tires moving fast enough to keep the temperature up. So the higher the temperature, the stickier the tire, the higher the coefficient of friction for the tire. And so they'll swerve like that, or maybe at the drag strip you'll see them burn out, right before they pull up to the line. Well, that's warming up the tires. And so when you have a wide tire, that heat, most of it is going to travel through the tread. It'll go through the tread, not through the narrow sidewalls. And so you'll get a sticky, high performance, high coefficient of friction tire. The drawback to that being that you leave bits of tire behind when you drive and when you burn out, and so they'll wear out faster. As opposed to me, I rarely corner in the family minivan doing 100 miles an hour. Like, it just doesn't happen. And so the tires on my minivan have tall sidewalls and relatively narrow tread, so that the heat will actually dissipate out the sidewalls and increase the lifespan of my tires. So there you go. Little aside on why racing tires are wide and economical tires are narrow, is it has to do with the heat traveling through the function. And if you're a mechanical engineer, you'll get to learn all about that in your thermofluids class. So have fun with that. Let's get back on friction. Dry friction, equations, number of equations equals the number of unknowns. And all we have to do is check the equation of friction to make sure that our frictional force is less than the total frictional force available. So we're using a less than here, and I've switched over to my notation of FRIC, mainly because I find it clarifying to me and also mildly humorous. So it's less than mu s times n, right? Because the maximum amount of frictional force it can get is mu s times n. If it goes above that much force to keep it in place, it'll actually slide, and so things move. Which brings us to our second case, which is impending motion at all points. Impending motion at all points. And so an example of that would be something like, if we look at my little block here, I can actually increase the angle of the ramp until that block on top, see it start to move? Starts to, something's going on, it's acting a little stuck. Until it starts to slide. You'll see how it's sliding now? Okay, so I'm going to back it off just a little bit, and I'm going to get it right to where it's about to slide. So if I do any more increase, it'll start to move. But remember, this is statics, nothing moves. And so we're right at impending motion. And so in this case, it'll take the number of equations of unknown, equations of equilibrium, plus the equation of friction to equal the number of unknowns. Okay, so here what we could do is we could figure out where what that frictional force actually is, right? And so that would be, it would be maxed out. And so our friction equation would become something like this: Fric equal to mu s times n, mu sub s times n. And so the idea is that when we do this, that lets us calculate one more unknown in our system. All right, so that's so we got no impending motion where equations of equilibrium are enough to get it done. We have impending motion at all points where the number of equations is equal to the number of unknowns, and we just have to set the friction equation equal to mu sub s times n. And then we can have the situation where we have impending motion at some points. Okay. And so in this case, we can look at a little example here. I have two blocks, okay? And the question is, as I crank this up, are they going to slide Are they going to topple over, which actually means the normal force and frictional force central location will actually shift to outside the block, right? So then they would topple, okay? Or is the bottom one going to slide, or is the top one going to slide off the bottom one? So those are all ways that it could move, right? But only one of those is actually going to happen, because the other two or other three types of motions will be less than their critical amount. Basically what it amounts to is we got 3 or 4 different ways this thing could start to move, but it's only going to start moving in one of those cases, and the other 3 cases would happen later, or will actually never happen at all, because once it starts moving, everything changes. We're even in a different course. We're in dynamics at that point. And so in this case, where we have impending motion, at some points, the number of equations of equilibrium plus the number of equations of friction is going to be greater than the number of unknowns. Okay? And so if that's true, what we need to do is we assume one case, and then we check the rest. So we could go through and we could say, okay, of the different ways this could fail, I have a toppling case, I have the 2 sliding together, I have the 1 sliding off the top, and I suppose that could rotate off like so. So those are all potential options. I would make a guess, meaning set, say, the equation of friction between the blocks equal to 0, right? Do all my equilibrium equations. I'll have equations of equilibrium for this block and for this block. So that's up to 6 equations of equilibrium, plus the 2 toppling cases, plus the 2 equations of friction. So now I'm at 10 equations, except I only have 7 unknowns. Now, you can trust me and we'll look at that in class. But the idea is that I would need to pick one of the cases, set it equal, and then check the other 2 cases. Make sure that it's not toppling either way and it's not sliding on the ramp. And so that would allow me to solve for the impending case at some points, right? So I'd have to pick the one case and check the others. It's a little bit like the problem you did on your homework where you had a load applied to 2 chains and the chains had the same capacity. You had to decide which chain you thought was going to break, set it equal, and then check that the other chain was less load than that. It's exactly the same idea. All right, so that's dry friction in a nutshell. I think I've taken too long on this video. So we got dry forces on dry surfaces resisting motion. We've got our equation, which is actually an inequality. The friction force has to be less than or equal to mu s times n. No impending motion means that we can do everything we need to do with our equations of equilibrium and just check to make sure that our friction inequality is okay. Impending motion at all choices, or at all points, we're going to use all of our equations of equilibrium, and we're going to set our friction equation as equal. And then impending motion at some points, we're going to have too many equations, so we set one as equal and then check our other potential failure mode equations. So with that, I look forward to seeing you in our class, and we'll work a problem together. Thanks.